For this video, I just wanted to walk you through this Chapter 1 project that you guys just finished up. I graded it. Your grades are now posted. So I wanted to show you what I was looking for with each of these different, with these two different projects in each of their parts. So hopefully it can answer some questions you maybe had. And if you still have questions, please feel free to reach out. So for this first little bit, I just started with asking you the question, what is a derivative? And what I was really looking for was just the words I've already forgot a letter, instantaneous, oh my goodness, my handwriting is so bad. Pop, pop, pop. And what I was really looking for was just the instantaneous rate of change. Now, a lot of you guys mentioned the word rate of change. I think everybody talked about the rate of change, but I needed something in there talking about how it's the rate of change at a specific point, or the instantaneous rate of change. If you just said, oh, it's the average rate of change for a function, average rate of change and instantaneous rate of change are very different things. So that's what I was looking for there, and that was a point each for each of those different pieces. Next, I wanted to kind of walk through the process of calculating derivatives. How we started by just estimating derivatives by using average rate of change, and then we looked at using limits to calculate the derivative, and then using our rules that we learned for part C. So for this first part, I wanted you to come up with 3 increasingly smaller intervals approaching this x equals 1, and then find the average rate of change. Okay, you can find average rate of change using the difference quotient, right? The difference quotient is 1 plus h minus f, well, in our case, because x is equal to 1, over h, where h is your change in x. So whatever your interval is, right, or size of interval. You could do it that way, or you could use average rate of change. You can also calculate average rate of change this way, right? F of x1 minus f of x2 minus f of x1 over f of x2 over x2 minus x1, where then you're just picking 3 different x values that are close to x equals 1. Okay. Well, a lot of you guys, I think everybody did it this way, and I did it this way as well, where I can choose 3 different my 3 different interval sizes I chose to be 0.1, 0.01, and 0.001. Okay. So once again, I can use either of these different methods to solve for it. This one, I would just do f of 1.1 minus f of 1 over 0.1, and you get 6.3. When I'm talking about f, I'm talking about my function. So if I dive into this a little bit more, right, which I expected you to do, I wanted to see your work on this, okay? I should see 3 times 1.1 squared minus 7 minus 3 times 1 squared minus 7, okay, over 0.1. This gives me negative 3.37 minus a negative 4 over 0.1, which is about 6.3, okay. So that's my average rate of change for h equals 0.1. I get 6.3. And then I can do it again, but for 0.01. Okay. If you use this process, guess what? You're going to end up with the exact same calculation. It's going to look very, very similar if you do it this way. Okay. Regardless, if you do it again, which once again I expected to see work for it, you should get 6.03 for 0.01 and 6.003 for an interval of 0.001. And that's what I was looking for on that one. So point for having 3 intervals, point for calculating f of 1 correctly, and then 3 points for each of these. Okay, well next we wanted to use limits. Instead of estimating using really small intervals, let's let that interval approach 0. And so if I'm using my difference quotient, I should have the limit as h approaches 0. That limit's important because that's the whole point of using limits here. Or of being able to actually calculate, because we're letting the change in x approach 0. So my difference quotient should look something like that. Now, some of you guys forgot that we were doing this at x equals 1 and just had the difference quotient in terms of x. That's actually fine as long as you remember at the end to plug in x equals 1. But because it actually gives us a specific x value, we are going to do this difference quotient with at x equals 1. So with 1 here in for x. Okay, well, what does that give me? I'm going to keep this limit throughout, but I can't plug in 0 for h yet until I get rid of this h in the denominator. I have to eliminate that first. So let's see what we get. We get 3 times 1 plus h squared minus 7 minus 3 times 1 squared minus 7. Well, I actually already know what that piece is equal to. I know this piece is just equal to negative 4. Okay, so that's going to make my calculations a little bit, that's going to make that part at least a little simpler. This part, 1 plus h squared becomes 1 plus 2h plus h squared when I actually expand it out. And then over here I get minus a negative 4 over h. If I keep simplifying, I get 3 plus 6h plus 3h squared minus 7 plus 4. Well, guess what's 3 minus 7 plus 4? That all goes to 0. So all of my constant terms end up just canceling out, which is good because that leaves me with 2 terms with an h in it divided by h, which means I can factor out an h and cancel. And I'm left with the limit as h approaches 0 of 6 plus 3h. And then now that I've gotten rid of the h in the denominator, I can go ahead and evaluate it. I can plug in 0 for h, and I get 6. And honestly, you guys did great on part B. I took a lot of time on that, but you guys aced that part, so I wasn't really too worried about it. Last, we're going to just calculate the derivative using my nice rules that we came up with later in chapter 1. And this makes life way easier because I don't have to go through the difference quotient or estimate it all. So if my function is 3x squared minus 7, I can go ahead and take the derivative of this. But I have to recognize that I'm using quite a few properties when I do this. First of all, I've got 2 different terms separated by subtraction, so I'm using my additive property of derivatives. Next, I have a constant multiple in front of it, so I'm using the constant multiple property. Okay. And then what rule am I actually using? Well, I'm using the power rule, of course, to actually take this derivative. And what's my derivative of a constant? My constant derivative is just equal to 0. So that's how I evaluate this other part. So I get 6x minus 0, which is just equal to 6x. And we can see that when we actually evaluate this at x equals 1, I get 6, which matches what I was doing in the other parts. Okay, when I graded it, I was for sure looking for the additive property. I was for sure looking for power rule. And as long as you had one of these two, I counted it. But if you're missing both of those constant properties, I took off a point. Okay, let's get into the complicated ones. So, project 2 was more complex functions. That might have taken you some a little bit of time. Part A requires you to use the chain rule twice because this piece requires the chain rule and this piece also requires the chain rule. Okay, so we can go ahead and look at, but then I also had this minus 1. Well, guess what happens when I take the derivative of this function? What's going to happen to that minus 1? Since it's outside the square root, that's just going to go to 0. So I really don't have to worry about that minus 1 when I'm taking the derivative of this function. Okay. Well, let's focus on square root of u. If I take the derivative of this, I get 1 over 2 square root of u in the denominator. Why? Well, that's because this is u to the 1/2, and when I take the derivative of this using the power rule, I get 1/2 u to the negative 1/2. What does a negative exponent do? It puts it in the denominator. That's how it ends up in the denominator. So that means when I take the derivative of this, I get 1 over 2 times the square root of u. Well, u represents everything inside of the square root. So I'm left with this. Made it a little bit bigger than I needed to, so let me shorten that. Well, once again, this is me using the chain rule, so now I have to take the derivative of what u is. Well, what is u? U in our case is 1 plus 4x cubed plus 6x. Well, this in itself, taking the derivative of this, also requires chain rule. It requires chain rule for this piece. So when I use chain rule here, I'm going to bring the 3 down. 3 times keep the inside the same. Oh, I'm so sorry. This is a minus. This is a minus 4x. Minus 4x cubed. So minus, 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 minus. 1 minus 4x. Here, let me actually go ahead and just rewrite that. Okay, but then I decrease the power by 1. And then I need to multiply by the derivative of the inside. What's the derivative of the inside function? The derivative of that is just negative 4. Plus, and then the derivative of 6x is just 6. So I've got that on the outside. Okay. Notice this negative 4 doesn't affect the 6 because that 6x was separate. It was a different term. So when I simplify that, I get negative 12 times 1. Man, I keep wanting to put a plus. 1 minus 4x squared plus 6. And that is all multiplied here on the outside. And where is it going to end up? It's going to end up in the numerator. At that point, you'll notice that on top, both my terms are divisible by 2, so I can go ahead and divide both the negative 12 and the 6 by this 2 right here. And I'm left with negative 6 times 1 minus 4x squared plus 3 divided by, that 2's now gone, so just the square root of 1 minus 4x cubed minus, oh, that's a plus 6x. That should be a plus. And that would be your final answer. Now, when I was grading this, I really just graded you on whether you got the derivatives correct. And I didn't grade you on the simplifying. So don't stress if you simplified it wrong. Okay. Once again, if you have any questions on this problem, feel free to reach out and I can try and clarify it a little bit more. Part B was all about the quotient rule. It's just a lot of quotient rule. So with the quotient rule, you have to isolate your top function, isolate your bottom function. So my top function, my upper function, we'll go ahead and call it u for upper function, is x to the 5th minus x to the negative 2. And then my lower function, or my bottom function, we'll do L. L is 5x cubed minus 2x squared minus 4x. Then I want to take the derivative of both, right? Because I'm going to need both derivatives for this. So u prime is 5x to the 4th, right? This is just power rule. Bring down the negative 2. Negative times negative 2 gives me a positive 2. X to the subtract 1 to the power. I get x to the negative 3. The derivative of my lower function is just, let's see, 15x squared minus 4x minus 4. And now I can put it all together using the quotient rule. So quotient rule is your lower function times the derivative of your upper function minus, and then just reversed. So my upper function times the derivative of my lower function, 15x squared minus 4x minus 4. And then all divided by your lower function squared. Once again, I went ahead and graded you just if you got this far. So I did not grade you on whether or not you simplified this one correctly, because there's so many ways you could have gotten this wrong during your simplifying. But I did want to show you how to correctly simplify in case you're curious about this. First off, the bottom is simplified enough. Don't multiply that out. Don't make your life way harder. That's nice, and that's as simple as I'm going to get the bottom, so just leave it like that. But on top, what I can do is I can multiply these terms out to see if I can combine like terms. So let's do that. This is going to take me a good amount of time, but see if you can follow along. So for this section, so let's start with this section right here. I get 25x to the 7th plus 10 minus 10x to the 6th minus 4x to the negative 1st minus 20x to the 5th minus 8x to the negative 2. You might be wondering where this constant 10 comes from. Where does this one come from? Well, that comes from doing 5x cubed times 2x to the negative cubed. 5 times 2 is 10. X cubed times x to the negative cube. That's 3 x's on top, 3 x's on the bottom. They all cancel out, so you're left with no powers of x. So that's why I end up with a constant. Okay, next. So now let's look at this piece. When I multiply those two, remember, after I multiply, I'm then going to subtract them. So I get minus 15x to the 7th plus 4x to the 6th plus 4x to the 5th. These end up becoming positive because you've got this negative canceling out with these negatives. Okay, keep going. Plus 15. Once again, that's because I have an x to the negative 2 times x to the positive 2. Minus 4x to the negative 1st minus 4x to the negative 2nd. Okay, and that's all still over. Once again, don't mess with the denominator. Just leave it the same. Now, I do have like terms, right? I've got a constant term there. I've got a constant term there. I've got an x to the 7th term. I've got an x to the 7th term. So every term has a like term that I can combine it with. So after I combine it, I'm left with the final derivative of 10x to the 7th minus 6x to the 6th minus 16x to the 5th plus 25 minus 8x to the negative 1st minus 12x to the negative 2nd over, and then the denominator is still the same. And it's not going to let me write anything else. Well, the denominator is still the same. So just look at the denominator. Some of you guys might be thinking, well, why can't I take some of these negative exponents and put them in the denominator? Well, the reason why we're just going to leave it like this, is because these are terms that are separated by addition and subtraction. When you've got terms that are separated by addition and subtraction, I can't do a lot of the handy rules of like moving exponents to the bottom, right? I have to treat these terms as completely separate. And so I'm just going to leave it like this. But that's what I get after I simplify. Once again, reach out if you're still not clear, if some of the stuff still isn't clear, if you have questions about your Chapter 1 project in particular. But good luck with Chapter 2, and I'll do a similar video like this once you guys have finished the Chapter 2 project. Have a great week.